All right, this is our second set of notes, and we're going to start by talking about average rate of change, which is abbreviated AROC or AROC. I believe we're allowed to use that on our AP exam as well. And average rate of change is something that we will be looking at all throughout the year. It's all over our AP test, and it's a pretty big concept, average rate of change and just rate of change in general for calculus. So average rate of change between any two values is really just talking about slope. So we just finished talking about slope in the previous notes, just the slope between 2 points. It's basically just another way to write the formula. We wrote a bunch of different ways to think about slope in the previous set of notes. So here's one more. The average rate of change formula, instead of m equals, it's like AROC equals. You've got 2 points on a function. So take a look at this curve here. Let's just mark off 2 points. I'm going to put my points here and here. And let's call the point on the left is at an x value of a. The one on the right is at an x value of b. And let's say this is like f of x as the function. So the height of this point would be at f of b, and the height of this point would be at f of a. All right, so if you take a look at this average rate of change formula, this is still just saying what's the change in the y value compared to the change in the x value. So instead of y2 minus y1, it's f of b minus f of a. I know we haven't talked about function notation officially in this class, but you've seen it for years, and that is upcoming. And then it's over b minus a because that's just subtracting the two x coordinates in the same order that you subtracted the y's. And sometimes you'll be asked to interpret an average rate of change. You do this in stats as well. So because this is not the exact slope, especially if you have a curve, this is an average slope between these 2 points. You can see that like the slope between these 2 points does not match the way this graph actually curves. So you need to throw in a phrase on average, because this is not a perfect representation of this graph between these 2 points. But on average, in context, you would say the y values, I'm just going to say y's, either increase or decrease. Again, depending on the problem, this is an increasing slope versus decreasing would be a negative slope, by however many units. And then you would make sure you label as x increases by 1, or you could say, you could use units here. You could say miles per hour or centimeters per second or something like that. So then you wouldn't have to use the as x increases by. But basically, the important part is that we have on average, and then we have y's and x's in context. It's not necessarily often that you're writing this out, by the way. It's usually a multiple choice question, and you're picking the correct, like, do you know what the x's are in context? Do you know what the y's are in context? And have they done this in the right order? Here's a question we get a lot: context or no context. When is the average rate of change the greatest or the least? So be careful about this, because it's not always about the steepness of the slope. It's not saying which is steepest if it's asking greatest, or which is shallowest or less steep if it's talking about least. This is talking about the actual numbers. So look at the AROC, average rate of change, numbers. Like, list out the numbers that you're looking at, and greatest is the largest number. So that would be like the highest positive number. Or if they're all negatives, the one that's closest to 0. So greatest number is the greatest AROC. And if we're talking about least, again, it's not like the shallowest slope necessarily. It could be the steepest negative slope. So you're looking at the lowest number. It could be the most negative. It could be the closest to 0 if you only have positives. That's the least AROC. So we have to be careful of that. That's something that tripped people up a lot last year. Like, I'm thinking about, they're picturing the graph, which is awesome, but they're thinking about steepness instead of just numerical values. All right, this example has a scatter plot. So use the scatter plot shown below to answer each question. A scatter plot is just, we've got a series of points. You can see these happen to be connected by lines. It's not always like that. Find and interpret the average rate of change for the sales of Goodyear tires between the following years. So let's take a look at this graph before we get into this. So these numbers are sales in billions of dollars for Goodyear tires from 95 to 2004. 5 represents, T equals 5 represents 1995. So find the slope between T equals 5 and T equals 8. And I kind of like to draw it in sometimes just to say like, okay, it's going to be a negative slope. So this is asking for the average rate of change. And I don't really have function notation to go off of here, but I'm looking at these 2 points. These are kind of cluttered here. So I'm looking at these 2 points. So remember, you're going 8 minus 5. So it's going to be 12.6 minus 13.2 over 8 minus 5. Now we can use a calculator for these. We can also, I mean, this is something we could do non-calculator, but just to point some things out to you. If you're going to do this in the calculator, either subtract with parentheses like this, or do it in pieces, whatever. Maybe you're simplifying as you go. Or here's something that I did not know existed until like last year. So if you press alpha and then any one of these buttons up here, there's all kinds of good shortcuts. We use alpha trace a lot, but go to alpha y equals. And this n over d sets up a fraction for you. So if you're someone who struggles with parentheses, our TI calculators, if yours has this feature, has made life much easier for us and a bit less typing. So that's kind of cool. So anyway, it's negative 0.2. If we get a decimal that does not terminate like that, our general rule is to round to 3 places. That's for the AP exam. Okay, find the average rate of change. Done. Interpret the average rate of change. So I'm going to say on average, the y values, but not y values. What do the y values represent? They represent the sales. I'll say Goodyear sales. Did they increase or decrease? This is a negative slope. You can see the numbers are going down. So decreased by 0.2. I don't want to say decreased by negative because a negative decrease is an increase, right? So anyway, decrease takes care of the negative by this number. What is the label on this? Billions of dollars. So I'm tossing a dollar sign in front, or you could write billions of dollars if you want. Oops, I don't need an S on that. And then instead of like as X increases by 1, I would just say per year. That's what we're really talking about, right? Negative 0.2 billion dollars divided by 1 year is what we went with. What about between 10 and 14? So here's 10, year 10, here's year 14. This is going to be an increase. It's a positive slope if I do my math correctly. So again, average rate of change is 18.4 minus 14.4 over 14 minus 10. Now this one is just 4, right? 4 over 4, which is just 1. So how do I interpret that? On average, almost the same thing. Goodyear sales, they didn't decrease this time, they increased by 1 billion. Oh, I should have put in the previous one, sorry, per year from, what was 5 to 8? That was 1995 to 1998. That's important context. So I'm going to do the same thing here. Increased by 1 billion per year from, let's see, what is this? 5 is 1995, so 10 is going to be 2000 to 14 is going to be 2004. Okay. Was the average rate of change greater? Again, not steepness. It's about the number. Which number is bigger? Between 5 to 6 or between 7 to 8. Now, both of these are just a 1-year span. So when you do the average rate of change for the first one, you're really just looking at the change in the y values. So 5 to 6, was the average rate of change greater? So that's a decrease from 5 to 6. From 7 to 8 was also a decrease. So which one is greater? Even though it's steeper from 7 to 8, this average rate of change goes from 13.1 minus 13.2 over 6 minus 5. So that's just negative 0.1. So they lost $0.1 billion for that one versus the other average rate of change. And I know if you're looking at the graph, maybe you just already know the answer, but it says show the work. So I'm showing my calculations here. 12.6 minus 13.2 over 8 minus 7. So that's negative 0.6 divided by 1. Okay, so again, you're just comparing the numbers. Compare these two numbers, negative 0.1 compared to negative 0.6. The further down the negative number line you are, the smaller you are, right? Negative 0.1 is closer to 0 than negative 0.6, so it's higher. So which one was greater? Between 95 and 96. So the AROC was greater between 1995 and 1996. Was the average rate of change greater between the years 12 to 13 or 13 to 14? So let's take a look on the graph. Sorry, I'm going to get all of my all of my pen marks off of here. Clean this up a bit. Okay, so 12 to 13 is the one we're looking at. And then 13 to 14. Now, both of these slopes are positive, so which average rate of change is greater? In this case, it is the steeper slope. So when they were both negative, it wasn't the steeper slope that was greater, it was the shallower one. When they're both positive, yeah, you are going with steeper slope. So again, I'm pointing out steepness just to show that sometimes it connects and sometimes it doesn't. Again, this is more, there are connections to calculus there. But they say show the work that leads to your answer. So that's common on our free response questions as well. So let's go ahead and just show the calculations of the two average rate of change. So we have one average rate of change from 12 to 13. So that is 13 is at 15.1 minus 12, which is at 13.9 over 13 minus 12. So that's what I should probably be able to do that, but it is the end of the school year here. I'm recording this in May. So 1.2, so that's positive, 1.2. And our other average rate of change, by the way, if you didn't have a calculator, I like to think of these as like, what's 151 minus 139? Figure that out. And then toss in the decimals at the end, just FYI. Okay, so then for this one, let's see, going 18.4 to 15.1 from 13 to 12. So that's going to be 3.3. That one lines up nicely for me. Okay, so 3.3. So again, which one is greater? We're just looking for greater. So compare 1.2 and 3.3. Those two numbers, 3.3 is definitely greater. So the greater average rate of change is between, what was 13 to 14? 14 was 2004. So that's 2003 to 2004. All right. So this may or may not be the first time that you've really worked with regression. I feel like in Algebra 1, we do some linear regression, but it's been a few years since you've been in that course. If any of you are in AP Stats, you'll be doing this shortly, but again, probably not yet. So in AP Pre-Calc, there is a large focus on modeling and picking the correct model and looking at the relationship between any two variables. So we're going to be working with data sets throughout the year and using different types of regression on our calculators to figure out the best model. So a scatter plot is used to plot bivariate data. That's just a fancy way to say two variables, right? X and Y. The points are not usually connected by lines like they were in this last example. All right, so here's a data table. The data in the table shows the outstanding household credit market debt, capital D, in trillions of dollars from 1998 to 2004. Construct a scatter plot of the data. So you're not going to have to sketch this by hand. But I do want to show you how to get this onto your calculator. So they didn't specifically say this, but we almost never type in the actual years into our calculator. So let's say t equals 8, 9, 10, 11, 12, 13, and 14 instead of typing in 98, 99, etc. All right, so I have these steps listed out here. First one says enter the data into the table on your graphing calculator. So we're going to press stat. So let me split screen here. Try to get both of these to fit. All right, so press stat and then press enter for edit. You should see L1, L2, L3, whatever. So go make sure you're in L1 and we're going to enter the years. Again, we're entering those not as 1998, but 8. So press 8, enter, 9, enter, kind of like you could for a spreadsheet if you've ever worked in Excel. So all the way out to 14. If you type too fast, sometimes numbers get skipped over. So just double check that you did that correctly from 8 to 14. And then we're going to type in these numbers. So 6, 6.4, 7, 7.6, 8.4, 9.2, 10.3. Oh, see, I did that too quickly. 10.3. Again, I do a quick check. Those seem right. You're not going to have huge sets of data to enter in. Okay, so enter onto our graphing calculator. Done. How do I look at the scatter plot if I want to just look at this graph? So there's a way to do this easily without having to figure out what the window is and everything. So if you press y equals and you highlight plot 1, by default, it's probably set into a scatter plot. But just to be sure, here's something I guess I don't have on here. Instead of highlighting just plot 1, like if you're in stats, you're going to need to change this. If you're just in my class, you're probably going to be fine. But second y equals is also how to get it into a scatter plot. So let's do that. Second y equals. So this says plot on, plot off, plot off. They might all say plot off for you. So press enter. Make sure that's turned on. The first plot is a scatter plot. We won't use any of these others. These are histograms, box plots, other fun stuff. X list is in L1, Y list is in L2. If this says something weird for you, how do you get L1 and L2 on your screen? You press second, see how it's right here, second 1 or second 2, if those say something else. Okay, anyway, and then the important part, how do I get this to show up? Zoom 9, zoom stat. So anytime you have numbers in your stat list, if you press zoom and you choose option 9, the window will fit to whatever your stats are that you put in there. So press 9, and there's our graph, right? It looks like it has a bit of a curve to it. So I don't know if this is really going to be a good linear function, but we could call that roughly linear. Because we're in our linear chapter, let's go ahead and find a linear regression, a line of best fit. So again, here are the directions. So you're going to go to stat, and then this time arrow over to calc. So just arrow to the right. And then there are 2 places where linear regression is. It really doesn't matter which one you choose. I know that for AP stats, you usually have your equations in this form where A is the y-intercept and B is the slope. So we're going to choose that. Again, it should say L1 and L2. We don't put anything in for frequency list. And then here's an important thing. Store the equation in Y1. We're going to be using this feature all the time for more than just regression and graphing. So this is a really important shortcut that I need you to know, because we can absolutely not use rounded numbers to make predictions for values. So we want to have the full equation without rounding any numbers off in our calculator stored. So go down to store a regression equation, press alpha trace, and that's a shortcut to pull up whether you want your equation to go in Y1, Y2, Y3. I always choose Y1. So what this does is when it calculates the equation for the line, it's going to type it into y equals for us instead of us doing it by hand. Let's go down to calculate. All right. So I got this A and this B. I'm going to write them down unrounded. And again, I'm just noting that The calculator has this stored. So A is the y-intercept. Just follow the outline they give you 0.025. B is positive, so plus 0. Don't round this, 7107142857x. Now, we don't really have x and y, so make a quick adjustment here. Take a look at your table. It does tell us that the y value should actually be d. And since we're talking about years, it doesn't specifically say this, but we should probably use t as our input variable. So let's trade this out. D equals 0.025 plus 0.7107142857. Instead of x, let's put t. All right, so what did all of that do for me? If you press y equals, you should see a nice long equation in here. And look, they even didn't round our, this does round to 0.025, but they even have the unrounded version there. And it goes all the way out. And then if we press graph again, because we already did zoom fit, we should see our line of best fit going through there. So it looks okay, but I'm still seeing some of that curve. All right, use the linear regression model from example 1 to answer each question. So use the model to predict the household credit market debt in 2005 and in 2025. And then which prediction is more accurate? So first let's find these values. So in 2005, what is t equal to in 2005? So let's go back to what we said. 8 was 1998. So these must be years after 1990. So 2005 is 15 years after 1990, right? So in 2005, t equals 15. So d of 15 is approximately equal to, that would just be you plugging 15 into this. Now, you can type out all these decimals if you want to, or again, this is a super important skill that we'll use all year. Quit to the home screen. You can just press clear to get back to the home screen, or second mode. Your calculator can do function notation. D of 15. Now ours is y of 15. So go back to alpha trace, y1 of 15, and press enter. The calculator knows what y1 is equal to because we stored it, and plugging 15 in, this is what you get, right? So we're going to, for our final answer, we used our unrounded equation to predict this. So for our final answer, we're going to get 10.686. We always round to 3 places for our AP exam. And that's this year for pre-calc and next year for calculus. And then we need to label this properly. Remember, D is measured in, it tells you in the problem, trillions of dollars. So 10.686 trillion, and I already put the dollar sign in there. In 2025, what's t equal to then? So that's 20 years after this, right? So t is 35. So then d of 35 is about equal to, again, alpha trace y1 of 35, 24.9. 24.9 trillion. So we did the first part. Our AP questions often ask us 2 questions in one line, so make sure you've answered the whole thing. Use the model to predict those 2 values. Done. Done. Which prediction is more accurate? Explain. So we don't really know the accuracy of either one, 15 or 35. But this model was based off of a domain from 8 to 14. So which one is closest to the domain of the actual model? Well, 15 is much closer to this 8 to 14 window than 35 is. So I would say that the 2005 prediction is, we don't know, so likely more accurate, because it's closer to the domain, the inputs, of the model. The domain of the model is t between 8 and 14. I would say 2025 is much farther from this domain. again, we've only had one AP exam, and it hasn't been graded yet. So I don't know yet how much you have to write if this were an AP question, or what all would get you your 1 point earned from this question. So it's a good habit to get into, to just be thorough but concise if you can be with your writing. All right, residuals and residual plots. So you're not going to have to create one of these, but you are going to be shown residual plots and asked to interpret what's happening. So residuals and residual plots help you figure out, like, how accurate is this model that we're working with. We just came up with a line of best fit. I just said, like, hey, this kind of looks curved, like maybe the line of best fit. What if the trend continues to curve up and my line goes this way? That's not very accurate. So here's our scatter plot that we just saw. This is a residual plot. And before I get to the residual plot, these in L3, these are the list of residuals. So what is a residual? So a residual, let's put this up here where we have room. Residual is the difference between the actual output minus the predicted output. If you think about what that means, that's basically just saying, what is the distance between this point and the line? Or what's the distance between this point and the line, or this point and the line? And if the line is below the point, then you're going to get a positive residual, right? The point is higher than expected. If the point is sitting below the line and you subtract, you're going to get something negative. And so that would be like, yeah, the point is below the line. So if we look at these residuals here, the calculator can store them and calculate them for you. So the first point here is sitting above the line and it has a positive residual. So that little distance there is 0.2893. The next point is just barely below the line. It looks like the line goes right through it, but it's a little bit below. So the distance between the line and that point is negative 0.021. Now, distance, we always say, is positive, right? Like, it's absolute value of that. But the negative sign indicates whether your point is sitting below the line, and a positive sign indicates that it's sitting above. Okay? So how does that translate to a residual plot? Well, this is the line y equals 0 right here. And think of that as the line of best fit. If a point had a residual of 0, it would be sitting exactly on this horizontal axis. If a residual is positive, like here's the largest, one of the largest positive residuals, and here on the other end is a positive residual. So this distance here is 0.2893, and this distance is 0.325. And this distance, 1, 2, 3, 4, 1, 2, 3, 4, that's this one, is negative 0.243. So the residual plot is just basically kind of like zoom in on this and shows the relationship between the line of best fit and what's going on here. So what do I do with the residual plot and the residuals? Well, you're looking for small residuals. So let's see. Let's answer this question. Is the model a good fit? Is it accurate for the data? Well, based on the residuals, we want small residuals, meaning we don't want huge spaces between our line of best fit and our point on the graph. Now, they look kind of large here in this context, but take a look. The line looks like it fits pretty snug within those points. Small residuals relative to y values. The y values range from 6 to 10, and the residuals, the largest one is 0.3. That's pretty small compared to 6 or 10. Okay, so small residual is good. But then there needs to be no pattern in the residual plot, meaning it should look like you just dropped these points on the page and they fell like that. And so it's hard for me to believe that they would fall into this nice parabola pattern. I was saying that I thought the graph looked curved. It could be that a quadratic model is more appropriate than a linear model. So no pattern in the residual plot. So for us, there is a pattern. It looks like a parabola maybe. parabolic pattern. So we would need to say maybe a quadratic model is more appropriate. Now, as we get further in the year, we'll look at ways to make that decision. Is quadratic better than linear? But yeah, for now, I could say, well, the residuals are small, but I see a bit of a curve to the scatter plot, and the residual plot has this kind of parabola type pattern. It is hard to tell with such a small data set, but that kind of shows that maybe the linear model is not a great fit. All right, let's look at just some other types of AP questions. So I have adapted these from AP Classroom, things that I found. So the table below represents the linear function, f of x. We're going to see something like this in our first AP Classroom assignment. Without a calculator, use the data in the table to find f of 9. If I had a calculator, I could just run linear regression, do my y1 of 9 thing, and call it a day. I don't have a calculator with this. Okay, so I do know that this is linear though. So what's the slope? Let's see. The slope or the average rate of change between these points is 11 minus 2 over 5 minus 2. That's 9 over 3, which is 3. Now the slope should be 3 between any 2 points that I pick because this is linear. 20 minus 11 is 9 over 8 minus 5 is 3. So yeah, the slope is 3. I can create the model for f of x. I don't have the y-intercept, so I'm not going to do y equals mx plus b, but I have 3 points on the line, so pick any 3 that you want. The point 2, is on the line. The point 511 is on there, 820. But I could say y minus 2 is equal to 3 times x minus 2. And I want to find f of 9. So that's when x equals 9. Find y. I know we haven't officially talked about our function notation yet, but that just means plug in 9 for x and calculate y. All right, so y is equal to 3 times 7, and then we're going to add 2 to this side. So f of 9 should equal 21 plus 2, 23. I know I used x and y because I was just writing a linear equation, but you could change this to f of x or whatever. It doesn't matter. We see tables like this in calculus all the time for number 6. So the table below shows the average rates of change for various intervals of f of x. Now this one's tricky, and again, I wanted to practice this before I let you loose in AP Classroom, but you'll see something similar to this again. Now, the average rate of change of f of x, the slope is 30 between x equals 0 and x equals 1. It doesn't mean it's like 30 per unit from that span. So here, the slope is 8 from 8. Let's do that. Let me write it like this. Per unit across these 4 units, right? So here's what we really want to look at. Over which interval does f of x increase the most? They're trying to trick you and say, oh, 30 is obviously the biggest number. Done. Call it a day. Greatest average rate of change. But you have to look at the span of x's. If you were graphing these points from 0 to 1 on that interval, the delta y is going to be a slope of 30 from the x values 1 minus 0. Right? So that is a delta of 30. But what about from 1 to 5? What's the change in the y going to be? We have a slope of 8, but the x values are changing from 5 to 1. You're going across a span of 4 x values. So what's 8 times 4? 32. So already this one's out. 32 is the largest increase for the y values. When does f of x, when does the y value increase the most? So right now it's here. Now the next one I shouldn't even have to do math on. It's negative 40. That's a decrease. So now it's a decrease in negative 40 over just one interval from 5 to 6. The last one I don't have to do either. This last one is not a decrease. It's 0. So there's no change in the y values from 6 to 10. Okay, so f of x increases by 32 from x equals 1 to x equals 5. Just looking at this table, it's hard to understand that that's what they're saying, but I tried to word this the exact same way that I saw in my AP classroom. So interesting. All right, that should set us up for our homework tonight. So please come into office hours if you have any questions.